So I'm going to talk about deferred acceptance auctions for multiple levels service. So this class of auctions, the deferred acceptance auctions, are very new. They're recently defined. And in order to explain how multiple levels of service is interesting, I'm going to spend some time initially explaining what single level of service work has been about. So in this binary accept-reject setting, what we have is a provider or a seller who's providing some services or resources to interested buyers. And the set of buyers are interested in acquiring the service, as in many of the problems we'll see here. And each agent has a value, so it's a single parameter, VI, that defines the value for that service, for getting that service. And what makes it a single binary setting is the buyer is either accepted or rejected. There are only two possible outcomes. There's no intermediate ways of dealing with this. And the constraints that we have some constraint. The resources are scarce in the sense that some subsets of the agents can be simultaneously accepted or served, but not all of them at the same time. So somehow we have to decide. Our goal is to serve a subset of the agents that maximizes the sum of the value, the total value. Right? So this is going to be, the main obstacle, of course, is going to be the fact that the values are going to be private, so we're going to try to elicit these values, and that's what these auctions are trying to do. So just to give you a couple of examples of what these binary settings are, one example is the single-minded bidders case in combinatorial auctions, where the seller has indivisible items, and each buyer is single-minded. They either want a specific bundle or nothing, right? So in that case, you cannot allocate an item to more than one buyer, and therefore you have a constraint over what subsets of the buyers you can serve. And your goal is to find the subset to serve to maximize the total value, the sum of the values. Another example is a knapsack auction where you have some constraint. Again, a capacity constraint. You have, for example, consider the seats in an airplane. You have a limited number of seats. Some family might want 4 seats. A single person might want just 1 seat. But you have a capacity constraint. You cannot just serve everyone. You have a limited number of seats. And again, that implies different subsets of these buyers that you can serve. Again, a binary setting, though. You either accept them or reject them. So for this class of auctions, Ilya Segal and Paul Milgrom recently defined in 2014, they defined this class of deferred acceptance auctions. They're motivated by the latest spectrum auction, where they were actually also used. And in that case, the constraint was that you have limited spectrum, and there are different constraints about interference that don't allow you to just give everyone spectrum, right? So you have these types of constraints, and you either accept or reject the different interested parties. And the interesting thing about this from an algorithm perspective is that these auctions just summarize the attractiveness of each bidder using just one score. And then they decide, based on that score, who to reject in a greedy manner. And I'm going to explain this further in more detail. But the great thing about it is that if you just design your auction using that principle, you're going to get amazing incentive properties. It's very appealing. So as long as you satisfy this structure, if you design your auction this way, you get really nice properties. And I'm going to list them later on. But these were specific to binary settings. They're not defined beyond that. And in fact, they're not defined for binary, for randomized auctions, and so on. So in many cases, binary is very restrictive. You're not just accepting or rejecting a buyer. There are different multiple levels of service. And again, let me give you a couple of examples. You can think of the Adword auctions, where the advertisers have different values for, if you search something, there's different slots with different click-through rates. People have values for clicks. But of course, you're not either accepted or rejected. You might get a better position or a worse position. There are different levels of service, right? And the existing definition of deferred acceptance auctions doesn't say anything about these types of things. A different example is, which I'm going to spend some time later on talking about, is if you have multiple parallel machines, identical machines, and each buyer is just interested in processing, has a job of some specific processing time, and is interested in buying time, essentially, in one of the machines. So you have, in this example, let's say 6 machines. You have these jobs over here, and you want to schedule the job and have it completed. And the thing here is that everyone wants their job completed as early as possible. So you can imagine they have some weight. Each buyer has a weight, which is the importance of the job. And the longer it takes for the job to complete, the worse the quality of service. Again, it's not binary. It's not like you're either served or not served. You can get different quality of service depending on what your completion time is in that schedule. That is the outcome of the allocation. And you can think of the cost of each one of the participants as its weight times the completion time that it gets in the induced schedule. And our goal in this case would be to minimize the weighted completion time, the total weighted completion time. So in general, the theme of this talk is going to be about first explaining some of the single level of service results, what has been shown already, and then how we extended the main result of our paper is an extension, a definition of deferred acceptance auction beyond single parameter setting, beyond binary settings to multiple levels of service, and also some examples. I'm not going to show you many of the auctions that we define. I'm just going to, at a high level, give you some intuition about what the new interesting algorithmic problems that arise are, because essentially it boils down to an algorithmic problem once you've defined the framework. Okay, so let me start with a single parameter setting. And in that setting, what we have is, again, let's think about single-minded bidders. That's a very good example to think about. You have a set of items. Each buyer is interested in a specific bundle of these items and has a value for it. And you have to decide which subset of the buyers to actually satisfy, who gets the items they want and who doesn't. And of course, this is also an NP-hard problem. You can imagine this is in general hard to solve. But our goal is to also solve an even harder problem where we don't know these values. It's not only the fact that if we knew the values, it would be hard to solve this. It's even harder because now we also have to deal with the fact that we have to elicit these values, convince the people to actually report their values truthfully. And there is an algorithm many of you probably know that works in this setting pretty well, and it's a very nice, simple algorithm and mechanism. Just order the bids in decreasing order of their value divided by the square root of the size. So everybody wants a bundle of size Si, and just take the square root of that, scale essentially the value divided by that, and that summarizes in one number, it summarizes the attractiveness of a bid. The larger the value, the more attractive it is. The larger the size, the less attractive it is because it's requiring too many items, right? So it's a kind of simplistic scoring function that summarizes the attractiveness of a bid. And then what you're going to do once you've done that, just order the bids based on that and accept them greedily. Accept the one with the highest score. Once you've accepted that, that means everyone who overlaps with the bundle that this buyer got has to be rejected. And just iterate. Just keep doing that. So it's a very simple, greedy algorithm, summarizes each buyer's attractiveness using that simple score. And then using that simple, greedy approach, then at the end just charges every buyer its threshold price. If you don't know what that is, it doesn't really matter. But essentially, it works. The good thing is that it is strategy proof. What you get is a mechanism where everybody wants to tell you, has incentive to report the true value. And you get these approximation factors. So if D is the maximum bundle size, and M is the number of items, you get D approximation and root M. And what is great about this is really you couldn't really hope. If you want a polytime mechanism, you couldn't hope for much better than that. So essentially, this is the best approximation algorithms that you can get, and you get truthfulness for free, right? So that was the greatest. It was one of the first, if not the first, algorithmic mechanism design paper by Lehman, O'Callaghan, and Shoham. So similarly, so the deferred acceptance auctions are quite similar to this, but they're different in the following way. They go backwards. Rather than accepting greedily, say I'm going to accept that layer and then reject whatever I have to since I accepted that and keep going, I have to go backwards. And that is quite interesting, even if you don't care about the fact that it gives you amazing properties in terms of incentives. It's really interesting as an algorithmic problem. How do you design these backward greedy algorithms to make them work, get decent approximation factors? But before I explain the structure of what the algorithms need to be like, let me explain why you should be interested in this class at all, the deferred acceptance auctions. So what Milgram and Segal showed about this class of auctions is that they use an adaptive backward greedy algorithm. That means that at each round, once you reject someone, you can update the scores. They can change from round to round. And as long as you do that, as long as your auction, your algorithm satisfies these properties, then you get ascending clock auction implementation, which is really great. It means everybody just sees a clock rising price, and then whenever they're not interested anymore, they just drop out, right? So it's very practical. This is not a common property for many of the auctions. It satisfies weak group strategy proofness. It satisfies obvious strategy proofness. It has privacy preservation, especially for the highest bidders. They're never forced to reveal their true bid because you're going to just implement this as an ascending auction. And many more, and it's important to stress that VCG, and even if you could run VCG, which you cannot because it's NP-hard, but even if you could run this, mechanism, then it doesn't possess these properties. Neither does the forward greedy algorithm. So these are unique properties that make it very useful for high stakes, important auctions, and essentially it hides. It doesn't mean it's simple for the designer. You can do many intricate things in the background, but essentially the interface, what the users see, can be a simple ascending clock auction, right? So all the smart stuff can be in the back, and then it can be simple and obviously strategy-proof for the participants. So it's very, very interesting to figure out what we can do within this framework. And to formally define it, essentially it has a sequence of rounds, a sequence of stages. Initially, every bidder is active. So we're going to say A sub 0 is the whole set of bidders, everyone who's participating. And then while the set of active bidders, A sub t, at stage t, is infeasible, meaning we cannot just say we accept everyone. That means we have to reject someone. And we choose who to reject by using that scoring function that I mentioned, some scoring function that summarizes the attractiveness of each bidder. And once we choose who to reject, then the new set of active bidders is essentially what was active already minus the person we just rejected. So we greedily reject people. And where this becomes interesting, the definition is in what form can the scoring function take? If it was arbitrary, you can always simulate any algorithm you want. So there's some constraint there. It can depend on any public information, but the interesting constraint is it cannot, so a bidder's score cannot in any way depend on other bidders' reported values. It can depend on its own value. In fact, it's a non-decreasing function of its value. The higher the bidder's reported value, the higher its score, but it cannot in any way depend on everyone else's. So essentially, you look at each person, each one of the bidders in the vacuum, and you just come up with a score. You look at the scores, whoever has the lowest score is rejected, and just continue. Yes. And at the end of the day, again, the remaining bidders are accepted and they're asked to pay the threshold prices. So the interesting question is, can you design these backward greedy algorithms, efficient backward greedy algorithms, to see how you can, what approximation factors you can get? And in previous work, one of the interesting initial observations is that they're not even maximal. It's really hard. It turns out to be pretty tricky to design greedy algorithms that are backward, because you're rejecting things without knowing whether at the end of the day you had to reject it or not. You're being myopic. You're rejecting things, and then at the end of the day, maybe you had to reject whatever the initial bid was in conflict with, so it might not even be maximal. So you have to be smarter. So the simple scoring functions like the one we saw before, the LOS paper, a greedy algorithm, that scoring function, if you use it backwards, it doesn't work well at all. It is horrible. So you have to be smart. You have to come up with tricky algorithms. And one of the positive results in previous literature actually shows, so our previous results with Tim Roughgarden and Paul Dudding shows that we can get a D approximation and a root time approximation, so the best that we could hope for. Okay, so to summarize the previous results, so what we know is that a deferred acceptance auction for single-minded bidders, so the best approximation guarantees and extra incentive properties that we get them for free. And in fact, there are other results that I don't want to mention here, but what I want to stress for this talk, given the limited amount of time that I have, is that there are several open directions. So by the way, this is not, although this session is about revenue maximization, clearly now you realize this is not about revenue maximization, but that's where I was assigned. But nevertheless, for those of you who are disappointed, there are open questions related to revenue maximization. So if you're interested in revenue maximization, the question of whether you can maximize revenue and to what extent using these auctions is wide open. We have no results there. What about other special classes of single-minded bidders? We don't know anything there. Other types of constraints in the binary setting, approximation guarantees with priors. We're not using priors. You can use priors and be smarter about this. What about randomized deferred acceptance auctions? We don't know the extent to which we can use randomization to make these better. What about revenue maximization, as I mentioned before. So today I'm only going to briefly talk about multiple levels of service, which is one of the constraints that this framework has. But there are many, many open questions that I think you should be interested in, since there's a very limited work compared to how new this, how many open questions there are in this. And I think it's very interesting. So the main result that we have here with Evangelos and Tim, I forgot to mention it initially, so the courses are Tim Roughgarden and Evangelos Markakis, are the following. So we propose a generalization of deferred acceptance auction framework beyond binary settings. So what we do is we keep that scoring function. We still say we have a scoring function that summarizes the attractiveness of a bidder, but now we're also adding a clinching function, and that's the novel thing here, which essentially says as time goes on, people clinch better and better levels of service. But once you guarantee a level of service, there's no way back, which introduces really tricky, interesting algorithmic constraints, because you want to guarantee something early on, but then at the same time, if you guarantee too much, you'll run into infeasibility issues. And you cannot look further ahead into the future too far away. So what we do is, using these two scoring functions, the scoring function, the clinching function, rather than rejecting a bidder at each stage, we just finalize the bidder with the lowest score at the level of service dictated by the clinching function. So the clinching function says, here's the level you've clinched so far. If you're the one with the lowest score, you get the level and you're out, you're finalized. Right? But that doesn't mean you're rejected. You get whatever you've clinched so far. So you want to start clinching early on, but again, there's this wall you don't want to hit. There's a feasibility constraint at the end of the day. And like scoring function, clinching functions are non-decreasing, and we're using threshold payments. Again, you don't need to worry about this. You can just think of it as an algorithmic problem. How do I design algorithms within that framework? And we guarantee for you that the incentives, all the properties we said before, still work fine. And with the limited amount of time that I have, let me try to give you an example about the scheduling, how the scheduling problem would work here. Okay, so as I mentioned, we have these parallel machines, these 6 machines, and we have weighted jobs. We want to minimize the weighted completion time, which, by the way, again, is NP hard, right? So how do we do that in an ascending auction way, in a deferred acceptance way? That's a tricky thing to do. How do you implement it as an ascending auction? So first of all, a first good indicator of whether you want to start thinking about deferred acceptance is whether you have a forward greedy algorithm that works decent, that works well enough. In this case, we actually have one. So you have these, you want to minimize wait and completion time, and you have identical parallel machines. Then there's a simple algorithm, the scheduling algorithm, that says order the jobs based on their weight divided by processing time, and just schedule them in that order in the least busy machine available, right? And just keep going this way. And if you do that, you actually get a very good approximation, right? But now think about, forward greedy is easy. Forward greedy is nice. What about backward greedy? How would the backward greedy approach work now? So what you really want to do is you want to start at a very high completion time and start finalizing downward, which is tricky. How do you do that? So essentially you start at the level of service which is really poor, and the longer people remain active, you just guarantee better and better quality of service. And it's tricky again, so what I want to convey here is that you want to start, to get a good approximation, you don't want to start with completion times that are really high up. That's your approximation factor is going to fail. But then at the same time, if you start really low, the important thing to observe is that then you might run into an infeasible schedule. And the very important thing to remember is that your score cannot in any way depend on the weights or the values of the people that come later on. So you essentially have some other people you need to schedule later, and you have no idea what their weights are. So you have no idea how you can order them or kind of change them around. And being oblivious to that, you still have to somehow come up with a way to finalize those initial jobs first, and then keep pushing downwards. So be close to the forward greedy in some sense, but at the same time, ensure whatever you promise, that is going to work. And I'm going to really rush through the way this mechanism works, which is not the point. I think the main point is to understand how this is to my understanding, a new constraint in how you design algorithms, that you essentially want to push the guarantee to get a good approximation factor, but at the same time, you want to make sure it's feasible. And what we do is essentially we look at the fractional make span plus the maximum processing time of the things we haven't scheduled yet, and this is how we define the completion time. And proving the approximation factor is easy. Proving the feasibility was actually pretty tricky. The fact that you can keep going downwards, just updating this at every stage and making sure that this will remain feasible. And what we get is a 4.8 approximation, which is kind of interesting. So using this much more interesting ascending auction implementation, you can do scheduling with a small constant factor approximation. And to conclude, so what I showed is that we have, apart from the results I showed, we have a bunch of other results. Like, for example, for polymetric constraints, VCG is a deferred acceptance auction. So for instance, in the Adword setting, VCG is a deferred acceptance auction, so you get all these extra nice properties for free. You can get log M for multiple knapsack constraints. You can get, in fact, we also have an extension for multiple values, multidimensional types. And again, there are several open problems that I mentioned before, and let me know if you're interested in any of those. There are more questions open than answered. Thank you.